All right, this is a set of notes on the different the historical atomic models, and so I'm going to go through 6 atomic models that sort of developed through time and talk about how they are similar and how they're different and just sort of how the idea developed over time. One thing to comment on here is I've got this timeline and it shows these different scientists or the different models and when they were developed, and you can see something that's interesting here is that the periods of time between these different models is getting closer and closer and closer. And what that shows is an acceleration in the development of science, generally speaking, or the development of thought. And so I think it's interesting to just see this firsthand on a timeline that human beings are accelerating at the rate at which they figure things out. And it's something interesting and noteworthy. Generally speaking, actually from this timeline, though, also you need to know chronologically speaking where these different elements are, where these different models are, so make sure you kind of have an idea of the order that these fall in. So this, typically speaking, when people think of the atom, they think of this particular atom. This is actually not even our modern idea. This is what we call the Bohr model of the atom. It's pretty good. It has a lot of things that are right, but it also has quite a bit that it's wrong too. And so something to think about is like our modern conception of the atom is different in terms of what the general public sees as what atoms are like versus what the theoretical physicists and like really extreme scientists think the atom is like. So now I'm going to get into talking about the different models. This first one is created by a guy named Democritus, who's a Greek philosopher. It was a very, very long time ago, but what he had thought was he'd thought that basically, if you kept breaking things down into smaller and smaller pieces, eventually you'd get to this smallest possible piece. He called this Atomos, or something that can't be cut anymore. And so this is where the origin of our word atom comes from. And basically, he had this weird idea about atoms, and he thought that atoms were the same material, but they had different shapes and sizes depending on what they were. So for instance, if you had an atom of air, it might be something that is wispy and light and fluffy or something like that, versus if you had an atom of iron, it'd be like hook-like and everything would hold together because iron is such a tough material and hard to split and things like that. Or water might be something like smooth and slippery like pebbles or something like that just slide past each other because water is a liquid. And so he had thought atoms had these different shapes and characteristics, but that they were all made of the same material, and then when you got to the smallest one, that was as small as you could get. So then Aristotle comes along, and he tells Democritus that this idea of the atom is completely wrong, all right, and that he has this famous quote where he says, if the air was made up of atoms, then what would prevent these atoms from just falling to the ground, all right, and so he doesn't think that there's even such a thing as atoms. Of course, he's wrong. His 4 elements are earth, air, fire, and water that he talks about, but he doesn't think that these are made of atoms. He thinks that they're just these sort of natural elements that exist in different combinations in nature. So then Dalton comes back, and this is thousands of years later, and revives the idea of the atom. So this person, he was a very research-oriented scientist. Democritus was a philosopher. So Democritus didn't do any experimentation. He didn't have any scientific evidence to back up what he was saying. He just basically said, I think that this is a good idea. And he would argue for why he thought the atom made sense, but he didn't really have any evidence to speak of. Dalton, on the other hand, has a lot of different evidence, and he comes up with these different rules for how atoms and elements work. He says that elements are composed of atoms. So every element out there that they identify is composed of some singular type of atom, and that the atoms if it's all the same element, the atoms are the same. So all carbon atoms are the same, all oxygen atoms are the same, et cetera, like that. He said atoms of different elements are different, meaning no two atoms of different elements are alike, so you can identify what element something is based on what its atoms are like. He said that compounds are formed by joining 2 or more elements. The other thing is here, Dalton thought that atoms were small, hard, indestructible spheres. So it's oftentimes called the billiard ball model because he thought that they were these really, really hard, indestructible spheres, and that the different spheres had different properties based on what element it was, and that they were all different from one another for the different elements, but that they were all spheres still. Thomson came along and he kind of put a hole in something that that Dalton had said. Thomson found out that there was something smaller in an atom, and so this means that, you know, that original definition of an atom, which is that it's not to be cut, or that it's indivisible, is kind of incorrect, because what Thomson finds out through his work is that there are actually smaller particles in an atom. He discovers what are called electrons. So his model is not fully developed. He just knows that there are some electrons that are kind of floating around inside of a positively charged substance, and so what he came up with is something that's called the plum pudding model. Plum pudding is not something that we eat so much in the United States, and so lots of times it's called the chocolate chip cookie model to like try and make it make more sense, but the scientific name for it is plum pudding, so no plum pudding. The chocolate chip thing is just to help you understand what it means. But basically what it is it's like most of the atom is positive, and then there are these little negatively charged bits put inside of it, which are called electrons. He called them corpuscles. That name didn't stick. Electrons is what we ended up calling them. And so that was his idea. The next person in here is Rutherford. Rutherford had an experiment. He kind of had an idea before he did this, but what he did was he took some positively charged particles, which are called alpha particles, which are really just helium nuclei, and he shot them into a sheet of gold foil. All right, and so what he saw was that as he shot them through this gold foil, that most of the particles passed right through the gold foil. All right, some of them bounced off of neutrons. All right, some of them of the nucleus, the positively charged nucleus, and so he was able to determine that there was like a small, very, very small positively charged center to the atoms, but that most of it was empty space, and he kind of developed the idea that there was a small nucleus, and then electrons are kind of around the outside. And so those are the big things that we get from him, mostly empty space and a small positively charged nucleus. All right, he didn't have a huge idea in terms of where the electrons were on the outside. A lot of times he kind of thought it's like a planetary model, so that they're kind of going around, the electrons are kind of orbiting around the outside, but that idea is more associated with the next scientist who is actually a student of Rutherford's, who's called Niels Bohr. So Bohr came up with this idea where he said that the electrons are orbiting around the center, but they're orbiting in these perfectly circular orbits, and that these perfectly circular orbits are in specific places, which he called energy levels. And he had this interesting idea about the energy levels where he said it was quantized, which means that the electron can't exist between these energy levels. It's either at one orbit or it's at another orbit. It doesn't exist in between. And it's a kind of weird scientific idea that we don't normally think about, but this is what he had said about it being quantized. And so with Bohr, the things to remember is that he thought there were these nice circular orbits and that there were specific energy levels that things fell at, and that they couldn't exist anywhere in between because of this weird quantum idea. And this whole idea of quantum mechanics actually comes in more when we talk about something that's called the wave model or the modern model, or sometimes it's called the quantum mechanical model. Lots of different names for this, but it's kind of what we believe now. And so what happens here is that electrons are kind of complicated in the way that they move. As one element to them, they have a charge, a negative charge, which attracts them to the nucleus, but also as they fly around, they behave sort of like waves, and there's this really, really complicated equation called Schrodinger's equation, which helps to predict some of the different places that electrons might be in an atom, but it's pretty hard for most of us to understand that. I actually, myself, I don't understand all the math and the crazy quantum mechanics. And so what I know, though, is that basically based on this really advanced scientific mathematics, we can predict probable locations of electrons, all right? And that's what an orbital is. And so we say there are these different regions in space where electrons are likely to occupy. I've got a few different kinds of orbitals shown here. There's what's called an s orbital, which is like a sphere, and a p orbital, which is like a sort of a balloon that's twisted in half, and then a d orbital again is like 4 lobes, all right, coming out, and then we've got an f orbital is like 8 lobes. And the way that we get these shapes, it's not random. It's based on these really complicated mathematical relationships, but it shows where electrons are likely to be located based on this really, really complicated math. This page here summarizes some of the main points of them. So the two first people here, the Greek philosopher Democritus thought that the atom was indivisible, all right, and then Dalton also thought it was indivisible. Thomson discovered the electrons, so it turned out that it was not indivisible. Rutherford found that the atom was mostly empty space, and that there was a small positively charged nucleus. Bohr put onto that there are these perfectly circular orbits, all right, and then with the quantum mechanical model, we found out that the orbits are actually not perfectly circular. In fact, the word orbital sounds a lot like the word orbit, but it's not an orbit at all. All right, orbitals are these regions in space, okay, where an electron is likely to be, but it's not what you would think of as an orbit at all. And then we say, with this electron cloud, we say that there's just these electrons moving around and they collect in these certain spaces, and that's how our modern model works. If you're confused by this or if you want more information, there's a lot of information out there on the internet. I recommend that you browse around and read some different things. And as always, if you have any questions, make sure that you come in and ask.